In this video, we will explain the Python implementation of the anomaly detection using TensorFlow library. Here in this video, we are going to show you the implementation of the LOF, or the local outlier factor method. So let's get started. We will use Google Colab for this example. For this implementation, we will be using NumPy, TensorFlow, and scikit-learn libraries. The Boston housing dataset can be loaded from scikit-learn library. Here, in this part of the code, you are able to see how we have imported the required libraries such as scikit-learn, TensorFlow, and NumPy. And you can see that we have imported the Boston housing dataset from the scikit-learn library. The dimensions of this dataset, the Boston housing dataset, is 506 times 13, which means that it has 506 samples of houses in Boston, each of which has 13 different features. Some of these features include per capita crime rate by town, proportion of non-retail business acres per town, weighted mean of distances to 5 Boston employment centers, pupil-teacher ratio by town, and etc. So here we can see that the dimensions are shown, and one sample is shown here, which is sample number 1. Here in this part, we are trying to get the shape of the data and store it in the variables. As you can see, we are getting the shape, the dimensions, and the number of the samples of the features here in these lines. The next step would be to change the data type into tensors, since we want to be able to use TensorFlow functions for this example. As you can see here in these two lines, we have converted the data into tensors. In order to find the distance between 2 points in our data set, we will use the broadcasting property. At first, we need to expand the data twice, as you can see here in these two lines, in data 1 and data 2 tensors. These are the tensors that I'm talking about, these two lines. This broadcasting property is really precious because it will help us code faster. After the subtraction, we can find the distance pointwise by computing the square of the subtraction, then taking the sum over all features, and then taking the square root of that. In this way, it will help us to compute the Euclidean norm distance between every 2 points. You can see in these lines how we can find the Euclidean norm distance pointwise, as I just explained. So it's some kind of a pointwise Euclidean distance of the tensors that we have at the end. The distance tensor is the 506 times 506 tensor, which has 0 values on the diagonal, which shows the self-distances. So the self-distance is the distance of each point to itself, and that would be 0. And that would lie on the diagonal of the tensor that we have as the distance tensor. So this distance tensor is just keeping the Euclidean distances pointwise. In order to find the neighbors of each point in this part of the code, we have sorted the distances in an ascending way. And we have found the indices of the sorted values. We can always choose the k value in this method. So the k value is optional. In this for loop that you can see here, we have computed the k distance for each point. The for loop that you can see is the one that is meant to give us the k distance. The k distance is the distance of each point from its kth neighbor. So we need to remove the repetitions that might exist in the distance vector to find the kth neighbor. It must be noted that the number of the neighbors that have distances less than the kth distance might be bigger than the kth distance itself. since there might be points with similar distances. So we need to delete them here for the computation of the k-distance. But they must be kept and considered whenever we want to compute the number of the neighbors for each point. So they are considered and kept as the neighbors of each point, but since we want to get the k-distance, the kth value, which has the distinct distance from each point, we need to remove the repetitions. Since the first distance would be always equal to 0, which is considered as the self-distance, we need to subtract 1 from the number of the neighbors that we have here at the end. This part of the code is the most important part of the code, in which we try to find the reachability distance pointwise. At first, we initialize some numpy arrays and tensors that we will use in the for loops, as you can see here. This variable sum will hold the value of the sum in the nested for loop, and this IRDK and the inverse of IRDK are just empty lists that we have here, and we are going to assign values to them in the next steps in the for loops. The IRDK tensor is the one that will hold the reachability distance values in it. I must remind you that in order to convert a tensor into a numpy array, it would be enough to run a session so that the tensor would become a numpy object with determined value. This is what we have done here in these lines that you can see, in order to change the type of the tensor, which is called the distance tensor, into a value. Before running a session, it will not allocate any kind of memory or any kind of computation, or it will not do any kind of computation. So remember, nothing is done before running a session for the tensors. In this nested for loop that you can see, we are trying to compute the reachability distance such that for each point we consider its neighbors and compute the reachability distance using the formula that we already showed in the slides. Since in the next part for the computation of the LOF, we would need the inverse of the reachability distance, here we have assigned to it a list which is called inv IRDK. So we have also rounded the values of this IRDK, as you can see here, because we need a specific precision for that. So we consider a precision which will hold only 5 decimal digits after 0. Here you can see the IRDK values for each sample. As you can see, it is shown in here. So each time the IRDK list is just appended by the new values of the IRDK, which is for the specific sample and the sample number. So the length of the IRDK would be similar to the sample number that we have. This list will have 506 different IRDK values in it, and each time it is appended by one more element in it. So the last IRDK would have 506 different values in it. In this part of the code, we are computing the LOF value using 2 nested for loops. And we are using the formulas that we have already shown in the slides. So we have 2 for loops which will form a nested for loop, and in that we are going to find the LOF value, which you can see here. So this LOF is also a list that we want to append it each time for different values and different sample numbers. For each sample number, we will get one LOF value, and we would append the list that we have here with a new value. And you can see that we have LOF values for 506 different samples. It is printed out here. And finally, in this part of the code, we are trying to detect the outliers by comparing the LOF values. Outliers would have LOF values bigger than 1. And as you can see in the previous part, in here, the LOF values are sometimes bigger than 1 or around 1, and most of the times they are less than 1. So whenever they are bigger than 1, it's a sign of an outlier. So this is what we are doing here in this part of the code. We want to detect the outliers by comparing the values of LOF. If the LOF of that sample number is greater than 1, we would append the outlier list with the new sample number, which is the new outlier. And we have shown the outliers here in the output. The number of the outliers is 94 out of 506 samples that we had for the Boston housing data set. But remember that this is the number of the outliers whenever we choose k to be 5 for the k distance. If we change the k with some other number, this list and the number of the outliers would definitely change. So this value of k, which determines the neighbors that we have for each point, is very important for us. I mean, the window that we consider around each point is really important for us. And we should tune it to the value that we really require in our specific problem. Thank you all for your attention to this video. In this video, we have not used the normal methods or the pre-built functions for the anomaly detection, and we have tried to write the code for it ourselves.